next concept is drift current and diffusion current. Generally, in a semiconductor, the flow of current is due to two actions. One is drift and next one is diffusions. In a semiconductor, the flow of current is due to two actions, namely drift and diffusion. First we will see what is drift current. Suppose I am taking a semiconductor bar, either p-type or n-type. I am connecting to a battery with the terminals like this, plus, minus. So this is a semiconductor bar. So electrons exist and holes also. So I am considering electrons. So because of this applied voltage, electrons have negative charge. So all the electrons are attracted towards positive terminal. So all the electrons are attracted towards positive terminal. That is, all electrons try to move towards positive terminal. So the electrons are moving like this. So electrons are moving like this means what is the conventional current direction? Conventional current direction is always opposite to flow of electrons. So that is like this. Conventional current direction I. So here the current produced due to drifting of free electrons. Actually they are moving. Moving means drifting. So the current produced due to drifting of free electrons is called drift current. So, and the current direction is always opposite to the direction of drifting electrons as shown in figure. This is called a drift current. So, this is in a semiconductor or conductor. We can call it as a drift current. So, this drift current is mainly because of applied voltage. This is applied voltage. So, another category, another kind of mechanism for current flow is diffusion. That is diffusion current. This diffusion current is basically in a non-uniformly doped material. Non-uniformly doped semiconductor. It exists in non-uniformly doped semiconductor. That is, doping is not equal throughout the semiconductor. Suppose I am taking a semiconductor bar. Suppose I am dividing into two parts. Here doping is very high. Suppose the number of electrons I am donor impurity I am taking. Doping concentration is very high. Whereas here doping concentration is less. So in this area doping concentration is high. In this area doping concentration is low. So this type of semiconductor materials behave diffusion current exists in this type of materials. That is, the doping is non-uniform throughout the semiconductor. Because suppose I am using donor impurity, so all are electrons. So same material. same charges. So same charges always repel each other, and after some time, what happens is, even though if you dope with high and low concentrations in a particular area, because of same polarity, the electrons repel themselves and they will adjust, and the electrons move from high carrier density to low carrier density. High carrier density to low carrier density. That is, these electrons will move to here high carrier density. So these electrons will move to lower carrier density. So and the total distribution will become uniform. So nothing but here moving of electrons. So this will cause some current. This will cause some current, which is called diffusion current. So in a semiconductor, the current is mainly due to two mechanisms. One is drift and diffusion. So total current is drift current plus diffusion current. Remember one important point here is diffusion current exists only in non-uniformly doped semiconductor. So in a uniform doped semiconductor, diffusion current is 0. But drift current is possible in a semiconductor as well as conductors. So this is drift current and diffusion current mechanisms. Next topic is mobility. Mobility of charged particles. Suppose we know that even a doped material is electrically neutral. This is because of number of electrons equal to protons. So how many electrons you are doping means that much protons exist. That's why even though a doped material is electrically neutral. So that is, without any electric field or without any applied voltage, there cannot be any current in the material. Without electric field or voltage, applied voltage, there cannot be any current in the material. So if we apply a voltage, electric field E, then current flow will exist. That is, all the electrons will move with a speed, constant speed. Generally, this speed is known as drift speed or drift velocity. All the electrons move with a speed called drift speed or drift velocity. Generally, that speed or drift velocity depends upon the magnitude of applied electric field. So drift speed, I am indicating with Vp, is proportional to applied electric field. So the proportionality constant is mu E. So where mu is a constant of proportionality, is called mobility of the electrons. Mobility of the electrons. In general, it may be holes also. So in general, mu is in general mobility of charged particle. Mobility of charged particle. So mu is given by velocity by E. So velocity unit we know meter per second, electric field volt per meter. So mobility is equal to unit is meter square per volt second. This is the unit of a mobility. So mobility is measured in square meters per volt second. So it is a steady movement. Mobility is steady movement. So such a steady movement of majority charge carriers with some drift velocity constitutes a current. So this current is called drift current. So mu is equal to velocity by electric field. So these two relations are important. Here this is unit meter square per volt second or centimeter square per volt second, which is very important relation. This is called mobility of free carriers. The next concept is current density and conductivity. Suppose I am considering material of length L, so which is having large number of free electrons, L meters. The cross sectional area A meter square. This is free electrons we are having. Suppose I am applying it to a electric field E is applied, or voltage, some voltage I am applying to the material. So electrons are, if I apply electric voltage means electrons will move with a drift velocity. Drift velocity Vp meter per second. Suppose let T is the time required by an electron to travel L meters. Therefore, average drift speed is Vp is equal to L by T. Suppose capital N is total number of electrons passing through any cross section of the material in T seconds. Therefore, our total number of electrons passing through any cross section. So, N by T, number of electrons passing through any cross section in time T is N by T. N by T is number of electrons passing through any cross section in T seconds. Suppose Q is the charge of one electron. Therefore, the total charge passing. The total charge passing through any point is I. I is nothing but total charge is n cube by t. Number of electrons into total number of charge by time in t seconds, n by n cube by t. So this is the current in a time t crossing the material. So current density is J, ampere per meter square, is defined as J is equal to I by area, amp per meter square. Suppose if you substitute the expression J is equal to I, so total charge passing in a time t is n q by t is nothing but current into A, n q by t into A. But we know that phase velocity is L by t. Therefore, t is equal to L by phase velocity, L by drift velocity. Drift velocity is equal to L by t. T is equal to L by drift velocity. Therefore, J is equal to n cube by t is nothing but L by drift velocity into A. So this is equal to n by LA into Q drift velocity. So I am writing like this: n by LA into Q V. L is length of the material or length of the material or length of the tube. A is area cross section. So LA, length into area is nothing but volume. LA is nothing but volume of the tube or material. Therefore, n by LA is the number of electrons per cubic meter. N by LA is the number of electrons per cubic meter, and it is called concentration of free electrons. Concentration of free electrons, which is denoted by small n. So small n is equal to total number of electrons by volume. So n is equal to n by LA, that is number of free electrons by volume. This is important relation, concentration of free electrons. So if you substitute this relation in the above equation, that is we are having J is equal to n by LA Q into VB, drift velocity. Therefore J is equal to, this is small n q VP, phase velocity, drift velocity, n q v, but drift velocity is mu e. Therefore J is equal to n q mu e. These two relations, this is 1, this is 2. These two are important, n q mu e. So current density is nothing but concentration of free electrons, charge of electron, mobility, electric field. This is also expressed as J is equal to sigma E. J is equal to sigma E, where sigma is equal to n q mu. n q mu. So sigma is called conductivity. Sigma is called conductivity of the material and is measured in ohm meter inverse. Ohm meter inverse, because as it is a reciprocal of resistivity also we can write. So sigma is equal to 1 by rho, where rho is resistivity. So here if you observe this relation, J is equal to sigma E, here this is nothing but current density, this is applied voltage, nothing but conduction current is proportional to applied voltage, so which is nothing but Ohm's law. Which is nothing but Ohm's law. Another important equation is the concentration of free electrons is also calculated by using another relation, d mu by am. Here d is density of material in kilograms per meter cube, mu is number of valence electrons per atom, A is atomic weight of material, M is constant, which is given by 1.667 into 10 power minus 27 K. Generally this is the weight of the atom, which is a constant value. So by using this also we can calculate the concentration of electrons if the material properties are given, otherwise no need. Here the four equations what we represented, first, second, third and fourth, these are very important relations to work out problems. J is equal to NQV, J is equal to NQ mu E, J is equal to sigma E, sigma is equal to NQ mu.